Okay, ladies and gentlemen, good morning. So before we begin, I'd like to make a brief remark. I'm not a professional master of ceremonies, like they have me there, who mixes several languages, including Portuguese, Spanish, French, English, Mandarin, and so on. And at the same time, it makes everything look beautiful. So I will only speak in English. I'm sorry for that. It is with great pleasure that the University of Campinas welcomes everyone for the World Academy of Science Young Affiliates Network Meeting 2025. This international event in Campinas aims to connect renowned early and mid-career researchers, as well as emerging researchers from all developing countries, to discuss advances and challenges in science, technology, and innovation, focusing on how these areas can contribute. One of the highlights will be a thematic session dedicated to the contribution of quantum computing and artificial intelligence. Over the course of 3 days, we expect significant participation from experts from various fields, providing an ideal environment for intense debate and the exchange of experiences. These interactions aim to promote lasting collaborations essential for advancing the frontiers of knowledge. The event will also address crucial topics through roundtables, panels, and thematic sessions. Among the thematic sessions, we include biotechnologies for sustainable health, innovation, and inclusive societies, environment, evolution, and emerging viruses, responsible and strategic artificial intelligence for the common good, from equity and national strategies to quantum machine learning perspectives, and dynamical system and biomathematics. The new TYAN, TWAS Young Affiliates Network Executive Committee will be introduced, discussing plans for the mandate and exploring new areas of work to increase internationalization and cooperation. The event will also feature poster presentation sections where researchers can showcase their recent work. These activities are essential for generating concrete action and strengthening collaboration networks, enabling interdisciplinarity and dialogue between fields. The benefits of this event are immense, including the establishment of new collaboration networks, access to advanced technologies, and exchange of expertise that significantly expands the impact of research. It will also be an excellent opportunity for academic exchange and professional development through high-level lectures, offering new perspective on emerging topics. Diversity of fields represented, from mathematics and biology to biotechnology, engineering, computing, and agronomy, enrich the debate and encourage the search for innovative solutions to global challenges. So, before composing the opening table, I invite André Alcântara from SESI, Industrial Social Service, to say some words.
Boa tarde a todos. Vou pedir permissão para falar em português. Primeiramente, agradecer a oportunidade de estar aqui com vocês. Me chamo André Alcântara, faço parte e represento o SESI, que é o Serviço Social da Indústria. Agradeço o convite da nossa presidente da Sociedade Brasileira de Matemática, Jaqueline. Estou também com a minha amiga, Larissa, que de pé, Larissa, para que eles conheçam. Larissa faz parte, constrói currículo de matemática e ciências da rede SESI. E é um prazer estar aqui com vocês, os palestrantes. Vamos estar aqui esses dias acompanhando tudo que vocês têm desenvolvido aqui. E agradeço a oportunidade de falar um pouquinho do que é o SESI, né? O que realmente o SESI representa para a educação, tanto para a educação básica como também para a docência, o que nós estamos pensando. Então, nós somos uma rede. Hoje nós só perdemos para a rede pública do governo, política e, privada, fora realmente da alçada ali da educação básica. Então nós somos hoje a maior rede de educação do Brasil. Nós temos mais de 450 escolas espalhadas pelo território nacional e nós temos mais de 11 mil professores na nossa rede. Então estar aqui trabalhando com vocês, hoje o SESI se posiciona como uma referência de robótica e ciências. Então nós somos premiados em várias competições de robótica no mundo. Nós temos um grupo de mulheres e meninas participando da ciência, uma grande quantidade, né? Na última temporada que nós tivemos da participação na robótica e na ciência, nós tivemos 60% de meninas participando desse programa. Então, para nós é um grande prazer estar aqui também aproximando, né, o SESI, que trabalha com a educação básica, com as discussões da academia, estar aqui também ouvindo os colegas, para que realmente nós possamos proporcionar para os professores da rede SESI uma qualificação, uma preparação também. E eu acho que o nosso desafio, nesses dias que nós estamos aqui no Congresso com vocês, é cada vez mais aproximar essa questão da educação básica com o ensino docente. Nós temos muitos pesquisadores premiados, cientistas premiados, e nós temos ainda um índice baixo de alunos na matemática e nas ciências ainda que precisam ser desenvolvidos. Então nós estamos aqui também para criar esse elo de ligação para que não só nós possamos avançar na prática docente e também nas melhorias do ensino para a rede SESI, mas também de uma certa forma avançar e ser apoio também para as escolas públicas do nosso Brasil, que é tão imenso, né, com grandes desafios. Então agradeço muito a oportunidade de estar aqui com vocês e vamos estar aqui também à disposição caso vocês queiram mais informações também sobre a nossa rede. Então muito obrigado pela participação aqui e pela oportunidade.
Thank you very much, André. So now we invite the following to be on the board of directors for this ceremony. So I invite Professor Ana Fratini, Vice Rector of Research at Unicamp, on this occasion representing Professor Paulo César Montañé, magnificent Rector of Unicamp. Now Professor Helena Nader, President of the Brazilian Academy of Sciences. Professor Jaqueline Mesquita, President of the Brazilian Mathematical Society and the Chair of this event. Professor Tashirina Rabia, Member of the Executive Committee of TYAN. Professor Ricardo Miranda, Director of the Institute of Mathematics, Statistics and Scientific Computing, IMEC. Professor Plame Kushnikov, General Coordinator of Graduate Students at IMEC. And my colleague and friend, Professor Marcelo Terracunha, Head of the Department of Applied Mathematics at IMEC. So, before starting to speak, I kindly ask to keep your remarks within 5 minutes. So now, please, Professor Marcelo Terra.
Okay. Good afternoon. It's a very big pleasure to be here, especially to be the least important person in a table with the Sendo. So congratulations, this is a very important. And I'm here as the head of the Department of Applied Mathematics, and it was a great coincidence that I was remembering the time when I was younger and happier, that I was a member of an associated member, affiliated member of the Brazilian Academy of Science, and we were there initiating lots of things. One of them was a big discussion that never ends about internationalization. And in that event, we could come to a very interesting synthesis that internationalization is to bring to your home the good international ideas, the good international practices. And today I can announce that Unicamp, our university, has changed.
Shall we start? Are we ready to start? So good afternoon. Let's start with all the activities. This is the first one. We will have this plenary lecture today. Professor van der Laan Bolzani is going to be in charge of this presentation today. She is a Brazilian chemist at the UNESCO, University Estadual of São Paulo. Long records, so I'm going to read and just highlight a few of them. She's former president of the Brazilian Chemical Society. In 2010 was elected fellow at the Royal Society of Chemistry. In 2011 elected to the Brazilian Academy of Sciences, a member of the Brazilian Academy of Sciences. 2015 elected vice president of the Sociedad Brasileira para o Progreso da Ciência. 2018 Superior Council of Fundação de Amparo à Pesquisa do Estado de São Paulo. She was awarded in 2011 as ISC, UPAC. But the last thing, today she was, she received the news. She was included in the Elsevier ranking of the most important scientists in the world. So she's great news today. So without no more words, so please, the stage is yours. Professor Bolzani, welcome.
Good afternoon for all here. I'm sorry about my English and also because I am so nervous. It's not easy to talk about so long time for natural products. That is not a hard science. Even chemistry is involved in the hard science, chemistry, physics, but we work on the So I will try to show to you today something about natural products. Also, I would like to thank and congratulate Jacqueline. She's like inspiration for all young generation. That is very important. And also, I am so happy to be here with Helena Nader. She's great, she's excellent, and she's inspiration for me. So long time. So let me. Battery. So I'm going to talk about my area, but I also it's very important to show you here because this meeting is very important to young generations. You need to increase the numbers of young talents in Brazilian Academy of Science, in São Paulo, Academy of Science, and also International Academy of Science. And when you see, I was a member of the team in chemistry for two terms in the TWAS. And you see a lot of Chinese. So many Chinese. When you analyze about Brazilians, you count in the fingers. So it's our responsibility to be involved and to discover and to look for talents to indicate is very important. So this is here you count in the fingers also the women. So it's very important nowadays to incentivize young generation, women, because the top of career, most are men, and we need men and women working together with their hands to sustainable world. So I try to show something about the natural products that you have working in São Paulo State University, Institute of Chemistry in Araraquara. It is a very nice course. You have 7 grades in CAPES, so long, in chemistry, and you have a group of natural products. And I'll try to small or large because now I decided to work on peptides. So there is a outline of my presentation. I will try to show to you something about our history, because you need to understand, to look at the past, to understand now our environment and project the future. And related to natural product, you have a very sad history. So, molecular diversity along of our civilization also, the man, when discovering agriculture, a lot of diet, because nobody discovered or not known what is good or not. Some are venoms. So this long process of the adaptation in Earth was very important, and you have several history about the use of biodiversity, all kind of biomes. Try to see how nature is important for us. When you talk about Amazonian, that destroyed Amazonia, you are destroying the most important library, chemistry library, that men, Nobel, never know about or realize about the complex structure that the nature can provide for us. This is one model. Robert Woodward, Elias Corey, all Nobels, because synthesize this kind of very complex molecule, including this that is very complex. In Christine, that is leucemic. And now, to idealize how a step of creation was possible for both identify, synthesize these compounds. So nature is inspiration for us, and nowadays, mainly nowadays, because the destruction of Amazonia is terrible. You can figure, I'm going to the fair, in the middle of Amazonia, you can see the wood in the rivers, illegal. Is a tragedy. So, this I like this. It's very old. Published in 2015. But it's very nice because you have a very, very strong plant science and chemistry science on nature in China. The Institute of Medical Plants in China is fantastic. And they study a lot, and you discover artemisinin, how many molecules we can have similar to this in our biomes. So you need to prospect. But during so long time was forbidden to prospect plant material because you had biopiracy. It was a very bad situation that time. Our university was received multa, how to say in English, 5 million because we are illegal. Now it's okay, but the natural product chemistry in Brazil at this time is diminished a lot because it's very hard. Mainly because it's very expensive. In São Paulo it's easy because you need one leaf to determine by mass spectrometry NMR so long. But it's very expensive, the equipment that you need to have this to compare with database. So this is, I think this is the importance of our biodiversity. We also, FAPESP, during the first times of Biota FAPESP, invite both. Wonderful to talk about biodiversity, just to show you the importance of the biodiversity for us. But for us, I like this cartoon that was made by Professor Veport in Leiden. He's an excellent natural product chemistry. And you can see, when I saw one plant, in my mind, I saw so many molecules. This is the importance that you have, that I think that is a beautiful hiding of biodiversity. When I look for a flower, it's beautiful, everybody, but I like what is forbidden in that flower. That is very important for us, and also for survival of the biodiversity. So this is another problem. When you see the long time of civilization and all time using plants, you count in the fingers the molecule that became very, very important for humans. No? So you can see that from morphine, that was very known for everybody so long, is alkaloid, to be here with epidolex, that is phenolics for cannabis. And I don't know, because you are young, but Professor Carlini, that worked with this, and Elena maybe knows, he was to the policy, because he worked on maconha and cannabis. So cannabis is very important. And you need to study, because when you study a plant in some environment, in some biome, you can maybe the process of biosynthesis can be modified. You can produce different kind of metabolites. It's very just a model. This also is a timeline of the peptides that recently, 6 years ago, I decided to work on peptides because nobody in Latin America work on peptides from plants. It's very common to work on peptides from microorganisms, from bacteria, from virals, from marine, but from plants, no. And I believe that all plants have peptides. It's very important because they have a very strong connection with chemical ecology. That's adaptation and regulation of some plants in some environmental. You know, you have 6 different biomes in Brazil. This is the fantastic that you have. All these biomes so different. Everybody knows about Amazonia, but you know you don't have too much studies on the chemistry of Amazonia. During Professor Gottlieb who was my supervisor, my inspiration. You work at that time, but now almost nobody. So you have several different biomes to study. But why you need to project the future, understand now, see the past? When we Portuguese arrived here, discovery Brazil. It's not true. They had the roots and know that here you have Cesalpinia equinacea pau Brasil. That is very important wood that have a very, very strong rare. That is very, very, very great values to pay to the England, because Portugal at that time needs to explore, and this was the first piracy that you have. So this is the compounds. Give the Nobel Prize for Robinson, because his discovery is very nice, because Brazilian is a very unstable, and give this column. It's like you cut the tree and you transform this in this column. This gave Nobel Prize this, and you don't have anything more about this. Also, to discover the traditional of the Indians, they used plants. That's curare. Curare is nowadays is pre-anesthetic, that you have relaxed of the muscle. So it's very important, and you have several different drugs based in curare that it was used by Indians. This is a very nice, this is a very sad history. And during the SBPC in Bahia, in Porto Seguro, I take this photo that I was very impressed. That is the tint of this kind of a plant. That is giripina from genipapo. That is a fruit that I don't like, but it produces so many things. When this fruit in contact with the skin, they complex, and you have a reaction, and it's like a tattoo. It's very important tattoo because it's not forever. You can take this and provide another, because they have a time. How many patents you have about genipines? All in the United States. We don't have anything about this here. So this is a history of our lab. We celebrate last year, 25 years of this lab in Araraquara. Most are retired, me too, and they gave me a professor senior to still there. That's fascinating to work with nature. This is the model that you have in our lab. And also, I like to highlight, because it was in this one room in biology, in Unicamp, where we discussed the biota program. I was at that time, and now it's very sad because this program is a beautiful program related to biodiversity, and the committee is only these persons, very nice, Jean-Pierre, Leticia, and Gabriela. She's not chemistry or biology, but she's very important because try to study administration, something like this. But it means that the biota is not more, as Jolie, I like this phrase, ocean of data, river of information, stream of knowledge, droplets on the distance. This is important to study nature. I will show some example past that this is a very nice, because this is a plant of Amazonia, and you see the wood, this very, very, very important wood, very high value, very hard, very important. And this we study she was my undergraduate, a graduate master and PhD, and started postdoc. She now is a professor in USP Ribeirão Preto, and we study all kind of alkaloids. That's very complex molecule. And the most important, because when she presented the work in some conference that I don't remember, Professor Zenk, very famous in German about indole alkaloid, this very complex molecule. And you have more than 4,000 different molecules already isolated, but someone doesn't have biosynth. So it's very important to know the biosynth, how to produce this kind of compound to keep this in lab and synthesize. So this was the compound that she isolated in nature. It's amazing, it's so important. You are not chemical, but okay, you have oxygen is like a hydroxyl that is stable because you have imine. And natural glycoside is like protect this group as you do in synthesis. It's fascination. So this is very important. He was fantastic with this because if you know how to synthesize this, how is the process of biosynthesis, we are be able to produce this in lab. And it's very important because they haven't leucemic activity. It's okay, it's another example. This is just to show that Derek Barton got the Nobel laureate in 1968 work on piperidines, very rare piperidines. And at that time, they synthesized piperidines. So we discovered a lot of piperidines, alkaloids, very rare, in this kind of plant that's very beautiful, that you can see in the streets and the ornamental plants. It's very important, this kind of compounds. His student, Professor Bunatilaca, looking for in our lab to try to identify this compound, but try to synthesize. And it also is a very sad history, because you have a patent, you have a very, very strong activity. You synthesize several derivatives because the compound internalize acetylcholine, that is very important as acetylcholinesterase inhibitor, and you produce, and this was discontinued because nature doesn't produce anything for us. They produce for the plants. Biologically activity is not mean pharmacologically activity. So you needed to prospect, and this was because you needed 10 grams of compounds to preclinical to start clinical phase. And you have condition and nobody to synthesize 10 grams of. So this was discontinued. It is a very sad history. Maybe if you are in Europe, in the United States, who knows, this could continue. Even it's very hard. This is a preoccupation nowadays with the colleagues that in São Paulo, I know someone in São Paulo University that use plants in ritual, in the religious rituals. So you needed to have a very good taxonomist in order to don't mix it and then to drink everything that you can kill. You have, this is a traditional plant, but this plant that was worked by a student in my lab is very, very toxic. Yes. It's so long, you don't know about that history because it's so long before. But this guy, in the rituals, they're so violent. In the United States, you have a very nice experimental work about the rats that try to kill each other with this. So this is the plants that used by Indians is Banisteriopsis capi. This is the compounds that tryptamines. You map everything. This is the student that try to steal and try to prepare from mucronata, very, very toxic. Different species of the same plants, you needed to have a very good taxonomist in order to identify, because you know the chemistry, but you don't know how the behaviors of you can see. In this another student, we got 1,300 species spread out Brazil, because now you have a very nice condition. You put one leaf, you can be able to run a mass on a mar, and you have this very, very nice. So when you analyze and we prepare a doc and send it to the Ministry of Health, because Capi and Viridis, that is traditional, is okay. They have tryptamines, that is hallucinogens, but they don't have this compound that you see can minimal difference, but very, very toxic. So another study just to show to you that you have also several young women that is very nice to work in this area. And summarize all this part, you need to have, it's very important to stay in São Paulo. I coordinate INCT, and you have money here, but when you compare with the INCT in the other states, it's not. You need to several times. You need to buy here to send, because chemistry is very expensive to determine the structure. But it's very important that FAPESP can provide. And we also have some studies with companies. That is a very nice. I know, if you know, you go to Amazonia, it's very nice. This is Bacuri. It's used to produce juice, cream, is that not aggregate value. And this compound, when you see the bark that you put out, the bark also produce, this is not good, practically one pure compound. It's very important. This compound is morelloflavone, that was the price. This was a very important work did by Diane Castro. Now she's in the company, and she was in the undergraduate, I see. And this is a property nowadays of the Sunrise, that is a German company. Umbu is like my land. I am from João Pessoa, Paraíba, and it's very useful there. And we have award in 2006, because this, even fruits, if you see the chemical composition of this fruit, you can use in the school for kids, and also you can use it in a place for old people that have several antioxidants, very useful as to eat this kind of fruit. If you concentrate and you prepare farinha, how to say this? Flour, sorry. Flour is better, and you maintain all antioxidants. Is another, now we change to explore peptides. That's very important, just to see some peptides. Peptides, you have a small one that is named orbitides and big ones, and we are more interested in big ones because you can see the plants, but you can synthesize linear, and after that you can close by do 2 or 3 creation, and the result is very good when you have a good, nice activity. Just to pass to, because my time is finished. Yes, no? Everything is peptide that have a different structure in my skull. Very important you dominate this. Now I'm going to finish my dream. This is a dream. I'm old. Should be Brazil could have a natural product database. This is a dream. I went to ministry during the Márcia Barbosa was there. You talk a lot because it's very expensive. Why? All information that you have on natural products that are in the literature in several journals spread out in several mass, molecular, data of NMR, physical properties is from chemical abstract. You take 100 years looking to organize a database. So you discover that you are be able to buy this information of all compounds that isolate from Brazilian biodiversity. So this is a dream, but it's not so, it's a dream because it's very expensive. But you try, was the work of this, now she's in Ribeirão Preto, she's a professor, and this was a PhD of there. And in 2015, I looking for these nature reviews. I was fascinated. Unbelievable. You have something very important. Because when you see all database that you have, all the number of the entries in database, very famous in the world, very organized, you see Nubi, our lab, our data, says 640 compounds. So I went to Brasilia, I went to study and to try to organize this database, but it's very expensive, but the cost of 10 million real to get all information from chemical abstract. That is the most important database on chemistry in the world. So you need to liberate this to have we are in negotiation now. I don't know how to say, because our government went to the TV. I don't know if you know. He told that about the take money of university. No, the university is very important for society, the professionals. But FAPESP has a lot of money, and this money is not used by the scientists. So this is very, very, very bad situation. You need to pay attention about this. This is the model that you try to organize. If you buy this information that you have now, this number of compound is in 2022. If you show that you still putting compounds there, is more. It's a very, very valuable data if you have all this information organized. So let's go back to see. This is the publication about this. We have one in Latin America, very, very organized. We have several meetings about this. That's Professor Molina. That is a database on Latin America. It's not, but they have more condition. I'm not sure if it's condition to have speech to convince government. And also, this is very important nowadays. This was published, and our lab nowadays has a selo de quality system. Exactly. Thank you. Because all work developed in our lab is green. It's forbidden use chloride. The only solvent that you use is ethanol and water. And if it is necessary to go to the HPLC to isolate the determined compound that is necessary, you need to apply, and you have 1 liter or 2 liters to organize your meeting and perform all that you have without use, mainly chloride, that is very toxic. This is our lab in 25 years that I told you. It's very important to have projects, and we got a lot of data and also collaboration with companies due to have very good support from FAPESP. During the INCT that's finished now, that I am coordinated, and also with the CEPID coordinated by Glaucio Oliva, that all of you know. He is the coordinator of a CEPID, I'm a vice coordinator, and he is a wonderful person. And he was, I think, postponed to the next year, and they finished, because 10 years, now you have new CEPIDs in FAPESP, and also you have approved 1 INCT with Norberto Peporini Lopes, that I think will start in November, according to Adelaide, that is Olival, that is a scientific director of Sendo Pequim. And this is quite nice because it's from peptides. It started in 2004. I know him during one advanced school of FAPESP that I organized here in Campinas in 2011 with 5 Nobel laureates, and he came with Feringa. And now he submitted in European community a big project, and invited me to participate of this project. I was very happy because I started in 5 years only to study peptides, and we start to study these peptides. And now I discovered that this biodiverse, the part of Brazil is financed by FAPESP. So it's very nice because you have FAPESP here. It's easy to see when you have money from the yes, it's very difficult to manage. So this is the how to obtain this. The main objective of this biodiversity, that we are the only group in the Latin America, but they have in Canada, in the United States, in Europe, and also in Asia. This is some patents that you have. Someone in the companies, it's impossible to talk more about this. And also, this is, I think, in 25 years, our lab is in tune with the goals, sustainable development goals that we need to reach. Sorry, with my bad English. So, this is the conclusion. I think it's for all of us, it's fascinating work to be at the university, work with the young generation. I don't become old. All time, it's fascination. It's very nice. All time you try to discover things, you can discuss it. It's wonderful. Also, biodiversity is the source to understand the nature, but it's the source for us that to study chemistry, to see how you can discover new models and try to imitate nature. Nature nature doesn't produce anything for us, but you need to take the model and modify the structure. And who knows, you have so many things better for not so for health, but also food supplements that you don't know. There are so many plants that can be used. This is a very important moment of my life because I was honored with this journal that is the journal most important in natural products. And they produce a special number dedicated to this old lady because I work along natural products and with my inspiration what we. And also this week I received a note. I didn't know about this Canal of Ciência from Evento. I never know about this. And I say that my name was included in this gallery, in this database that I needed to see. I received a message and I think this is very important because I can inspire, how knows, the new generation, because the future is to see in our students how important is the study and also is the research, because in São Paulo, no, but in the country, you have a lot of Bolsonarists. That's amazing. You can believe that at the university you have people so democracy. I like democracy that you are good on the side for others, but it's not necessary to have to be so radical. This is the students and the collaborations. Without collaborations inside and out of Brazil is not possible to develop because you have so many collaborations. You send the students mainly with the people of the Austria and also Peter de Hoestein, that they come for our lab and you send the students for their labs. And also my family. I think they are my life. My family, my grandchildren, they ask me, why you are going to Campinas? I'm going to talk. Why you talk Campinas? Very curious and try to explain, but he didn't explain because always during the Thursday, a mommy and dad go to some place and they come to stay with me. I'm going to São Paulo to stay with them. This is all the support. It's very important. Thank you very much for inviting me with this broken English.
Thank you, Professor Zani. We have enough time for questions, yes? Let's start here. Pablo, carefully behave.
Good afternoon, and because you were mentioning all these beautiful compounds, especially from Jatropha, especially ones for cancer and malaria. Now, with so many gifted people in Brazil, I was wondering if the next step is to recreate the synthesis pathways in yeast, in Saccharomyces, because that way you could synthesize high yield of this compound. And I know the Chinese have been doing it for a while, but with Saccharomyces. So I was wondering if you have ever discussed the possibility of developing transgenic yeast for these compounds. Do you think that's possible?
I think it's a very nice idea. In the past, we tried to use Saccharomyces in some species of pepper that is working by Massucato in São Paulo University in chemistry in São Paulo. He's a very important in this area. I think he is the best in the world. Now he approved the INCT to work work with some kind of compounds of this plant, but didn't work at that time. But I think it's not work because we needed to study a lot. It's not necessary only to have the yeast, but you needed to establish all steps to know how this can work. It's a very nice biotechnology. But in euphobias that you have these peptides, the small peptides, okay, because they produce the plant small is easy because the molecular weight is like a natural product that you have. But when it's large, it's not easy. So you can synthesize, and after to close the linear peptide, you try several. One was tried with Saccharomyces, with a mixture with some reagent that I don't remember more, but they were quite nice. Now I have a postdoc from Fabesp, and she started to work on peptides, but you try to see how you can synthesize these peptides, not looking for the nature, because you know the procedure is okay. It's very small amount you need to synthesize. So the process, she starts 3 months ago. So you need to, it's very important, I think so. I cross the fingers in order to see if you can have good result using this, not only the reagent, but also to use yeast.
And I also was going through this question because you said that many people question the amount of money that you invest in science. But if your university said, okay, we have a pipeline of these products in Saccharomyces, and you're ready to synthesize them in an industrial scale, so this could be used to defend the science too.
Also, now you have one open position in chemistry, who knows, and was dedicated to synthesis. Who knows, you have some here to synthesis, because it's very important to be from synthesis, because it's easier. We are not a synthetic. So who knows when young women or men come to our lab and synthesize this kind of compounds. That's very important, because I'm not good in synthesis. We'll try, but it's not. It's very hard to study in synthesis. You know, no? Yes, it's very hard. I know some very important synthetic men here, Luis Carlos Dias, and also in São Carlos, and also, Luis Carlos Dias from here, Carlos Roque.
We can share all these opportunities, information about these opportunities in our network and website. So this is important for us to know. So, yes.
Thanks for your talk. It was very nice. From my question goes like from my point of view of someone who, I don't work in chemistry, but I have collaborated in several natural product studies from the biology part. And I always feel a little bit frustrated from the part that we always sometimes we find something and it's really promising, and sometimes we can collaborate with someone and go further, find the molecule that is doing that. And then that's it, we stop somewhere there because we don't have more power or money or to actually start some more trials, like in a bigger, so we know this has, for example, anti-malarial activity or anti-cancer activity, and then how, in your point of view, as Latin American researchers, for example, or as third world researchers, can we go from there to the next step of like actually going to like clinical trials and something like that? Because I always feel that we get there and that's it. That's our last.
This is a challenge.
What? Okay.
It's a challenge, I know, because when this is the point, I work with nature, with biodiversity, looking for the built behind in nature. Because I am a scientist, I want to know what the structure, why this plant produce some kind of molecular skeleton, and this is very important because when you think that plants, you need to looking for pharmacologically activity is completely different because plants doesn't, I believe, anything for us. During the process of adaptation, you see you have 6 different biomes. We study a plant, euphorbiaceae, that is small peptides from caatinga, that is a kind of cerrado, very dry, and from, I don't know how to say the plants in the south of Brazil. It's completely different, the biomes. Completely different, and they produce some similar compounds because they try to, I think the organism try to produce molecule to adaptation, to regulation, to also, you see that of the plants in Amazonia, in the leaves, you have a very important kind of aromatics that can block the sunlight that is very dangerous for plants. This is not for us, but it's very important when you discover something that you have activity. The problem nowadays is to find the companies because we are responsible for science and discovery in academics. You have a long process from the discovery, publish, and also if has some interest, that is technology, and after technology to transform innovation. For millions, you see one go to the end of these steps. That you see that the line of timeline that they produce, how long we also produce morphine that use until nowadays. During the COVID, it was used, and you have a problem in the market because morphine and derivatives. So you have Hudickley, he's from California University. 5 years ago, he produced one analog by synthesis. And now they have a company try to transform that in large amount. It's not easy. 5 years trying to involve in this process. This is the challenge. But I needed to, who knows, your discovery or a student using Saccharomyces that you can transform, but biotechnology also is very hard and depend on the lab. But I think it's not now our mission. Now our mission is a fascinating discovery, but after discovery is another step that may be the companies, and now they don't have the companies interested anymore in compounds from nature, in everywhere, in not only in Brazil, in developed countries, because it's easy to modify the structure of a morphine or vincristina, then looking for a new compound that you have put a lot of money to see if they can go the end of the process and was liberated by FDA or some other, or Anvisa or some other.
So another question here, very quick. My name is Rolando Gittens. I'm a scientist in Panama. And, it's such a beautiful talk. I come from a research center that also collaborates with Dr. Dorenstein and in biodiversity. And so, it's a fascinating field. It's so amazing that, you guys have been working with artificial intelligence and machine learning for a while,
yes,
and showing how important it is to reduce costs and improve efficiency. My question was actually related to Fabian's, related to, maybe not the technical aspects, but I wanted to know how easy or difficult has been for you, being a leader in the field, to collaborate with companies in a field that is so directly relevant, right? So pharmaceutical industries should care about this, biotechnology companies should care about this. Yes. How?
The best, I think, was very. When was the first program? So long time, maybe. Elena, she has a very good memories. Have a program for the government, grant, green and yellow. At that time, they have a lot of money in putting the companies. One was Europharma, and the second one was Este, Laboratório Este, that is very important pharmaceutical company. I think is the major in South America. And you have some project, but it's not easy. Why? Because they don't realize that to develop something, companies, as you have in Europe, in the United States, you need to have development of science for the technology to improve the amount, to modify the structure. That is not a competence of us. In our lab, you don't have the condition to synthesize. When I use synthesis, now you have a lot of, maybe some simple things is okay, but hard things to produce a new model of molecule is impossible. You need to go to Campinas and to see if the colleagues of Unicamp has condition, but all have a focus on kind of structure and model that are synthesized. So this is a process. And nowadays, most of the companies don't care more about the natural products. Yes, because I told it's easy to modify the structure. Then you looking for a new that's completely new, and you need to invest a lot of money.
Okay, thank you. Thank you so much for the nice talk. So I believe with you that I believe that plant produce compound for the defense, for environmental issue. So my question is, do you think that since you say that you are interested with peptide, do you think that plant produce all plant has peptide inside, or because this is because if I look in the literature, I understand that the last compound which was put on market was artemisinin in 1972. But since that plant does not, plant didn't produce anything else which was so interesting to be put on market. And you say that you are looking for peptide. Do you think peptide plant will produce an interesting compound called peptide?
You have after you give your email, have a very nice review in Nature in 21 about peptides. I believe it's not. In my mind, all plants produce peptides, but the difficult is the amount. How will that identify? Because it's a big molecule. In a mixture, with so many things, peptides. Now you have I think you have now a very, very strong database on peptides that you can compare. When you think that you have in a mixture, you have a mass, depend of the number of amino acids, you can have idea about this. If you have idea, based on the peaks that you have in database, it's quite nice because you can identify the noun. Because it's similar, you take off. So if you have 2, 3 depends. Sometimes you are be able to isolate it by your HPLC, but the amount is very small. If you need to improve the amount to performance, some assays, it's very difficult because it's not only to determine the structure. To me, it's okay because I'm a scientist. I need to see how the structure, but it's different when you're looking for something in the nature. Think about the properties of this molecule have for us. This is complex, very complex, but you have you told about Dorenstein. Dorenstein have a very, very, very nice database. I have a student, she took a PhD with me, and now she's a scientist. She was contracted because she's excellent. She was one of the leaders in young talent from the ABC, Brazilian Academy of Science. She was selected to the Lindau, that is a meeting with a Nobel laureate of very important students. And now she's working in the United States, but they have a database because they're looking for, not for only for looking for some drugs, but also looking some kind of peptides that can have some biological activity. That's quite different.
Bueno, tenemos lugar. We have a place for just the last question, sorry, and then finish.
So, I was very fascinated with the biodiversity component that you kind of showed and how this richness of this biodiversity has been discovered. One of the challenges that many countries have been facing is the preservation or the conservation of this biodiversity. And through our deeper explorations of all the homes, whether it is the genome or the proteome or the transcriptome, etc. So the issue is that the biological mechanism that we have started to understand, that the biodiversity decays, again because it undergoes evolution. Some evolution may not be positive. There might be inherent genetic mutations that a microbe can get in and that might reduce biodiversity. And it is very essential to capture that kind of a regressive mutation or kind of couple them to kind of interact so that they are made more stable in the sense that their survival is kind of ensured. So in the context of Brazil, is there any such effort to kind of preserve biodiversity based on the molecular mechanisms what we have been starting to understand based on the microbiomes and their diversity?
Nowadays in Brazil it's quite complex. Yes, because I have been twice a year in Amazonia. That you have a very, very important, because it's a equatorial forest. And that forest regulates the environment in several places because it's in the Ecuador, right? In the kind of species, they have a very special environment, biome, that create, and you see the destruction is huge. It's amazing. And because of the wood, the cut, because it's illegal, most don't have any studies about. Some species maybe don't have taxonomy. So you lose the information of the taxonomy, of chemistry, and also biology. And how you think, because nature is giving us information. It's impossible for us. idealize kind of compounds. If you have, I can know to you, porcinase, loganiase, and rubiase, you have indole alkaloid, because I work a lot. And you see that you prepare the primary precursors and secondary precursors, you are able to combine. You have several different kind of indole based on biosynthesis, but just one kind. But when you compare, it's very, very difficult. But I believe that if you have all databases, this is my dream. Because some plants that was worked and are spread out in several journals, if you get this information, you will be able to have new information about biomes. And so this can be very important for us to identify not only and compare with different biomes, even the same line, if in Ecuador, in India or in Brazil, and you can combine, because you did this with the malperiers in Africa and Brazil. And in one region, they are similar, even if the plant came from this, they don't modify a lot. I don't know if I respond, but...
Okay, I think we can keep discussing later. Thank you for your presentation, presentation.
Thank you very much. Thank you very much.
Okay, I think we'll just move to the next talk. Hola. Next talk is Professor Alexander Reilly Rocha. And please. Briefly, Alexander Reilly Rocha is a physicist by training, bachelor and master degrees in physics at the Universidad Estatal de Campinas. Since 2012, he's a professor at the Institute of Theoretical Physics in UNESCO. During the years, he was appointed as young affiliate of the Brazilian Academy of Sciences, also to the young affiliate to the World Academy of Sciences, associate member of the ICTP, and many more. So, please, Alexander, you can start your talk. You can use the mic.
Thank you very much. It's a pleasure to be here. Actually, it's twice the pleasure. First of all, because I'm a graduate of Unicamp, and in fact, when I entered Unicamp, I did physics. However, I don't know if it's still like this, but whenever you entered Unicamp, you entered in a joint program between physics and maths. So for a short period of time, I was also a student here at IMEC. So I've been back to FGW, which is 2 blocks down, but it was the first time that I give a talk here, so this is really a pleasure for me. The second reason is because, I'll be 46 next year, tomorrow, and I'm glad that TWAS still thinks that I'm young. So what I thought about doing was to give a little bit of an overview of what we do, but actually also give you an overview of what the field looks like when we're talking about computational physics, which is really my field of work. But before I start, so I'm a colleague of van der Leyen, and I'll do a little bit of advertisement. So we work at UNESCO, so van der Leyen is here. Araraquara here. And we're based in the city of São Paulo, so about an hour from here, really in the capital. And we only have 2 institutes in São Paulo, so it's mostly a university that's spread throughout the state of São Paulo. And we are the only 2 institutes in São Paulo, so it's the Institute of Physics and the Institute of Arts. So the campus is very, very mixed. And you definitely can see who is a physicist and who's an artist on the campus. So the institute is actually older than the university itself. It's actually turning 65. And it started off as a private institution and then was absorbed by the university. And all this to make a little bit of an advertisement. So as Marcelo Terracunha was making advertisements for IMEC, I'll do the same. So we'll have 4 open positions throughout this year. So if you're a theoretical physicist, you like computational mathematics or mathematical physics, or even if you're doing theoretical biology, we're very, very much interested in what you have. And so if you're looking for a nice position, this is the place to come. If you are working in theory, you know this brand here. This is the International Center for Theoretical Physics. It's based in Trieste, which is actually the same place that TWAS is based in. So if you've visited there, it's actually in this ICTP campus. And we have a branch of ICTP here, and we organize a large number of schools and events that are related to physics, maths, computational science, and also we're very much now interested in biological physics as well. So this is my advertisement, so if you're interested, come to work for us. I'm doing this both as a member of staff and also the director. And so with this, I'll start my talk just giving you a motivation. And if you're coming from any area of science, probably water is involved. So if you're in general physics, water is everywhere. If you're in biology, obviously water is everywhere. And I can say, for example, that if you take the most well-known biological molecule that we have, which is DNA, just because of the amount of water that is surrounding the molecule, the structure of the molecule changes. Or even if we're looking for life outside of our planet, we're looking for water. So all of this just to motivate you, I think, hopefully that you'll be interested in this talk, that we're only going to be talking about water, and it seems like something very simple, but I'll hopefully show you that it's not, and also it's extremely important. And for example, one everyday thing that you know, or every kid knows, is that ice floats on water. However, although this might seem like an obvious thing to happen, it's not. In actual fact, you would expect that the solid of a certain material is actually denser than the liquid. And this is something that you see most of the time. And so because it does not happen in water, it's called an anomaly. Actually, water has quite a number of anomalies. And so, as I'll show, I mean, it's a very complicated molecule and a very complicated liquid or solid to study. And we don't actually understand it very well. From a technological point of view, also water is extremely important. So if you're doing, obviously, biochemistry, or if you're doing catalysis, or if you're looking for clean energy, then obviously water is involved. It might be involved in a detrimental way because you don't want things to be getting wet most of the time. For example, if you're looking for solar cells, or you actually do things in solution in many other cases. For example, if you want to break water to form hydrogen as a fuel, form of fuel. So all of these things is things that I'm really interested in. And in particular, my group has been working a lot on the interaction between surfaces and water. And this is because a lot of chemistry happens at this interface. And so what we want to do is to actually look at the microscopic structure of water on these interfaces. So we really want to be able to somehow find a way to understand, if you put the molecules, the atoms in the right places for the solid and the water molecules, how these things behave in a very realistic environment. So try to get as little modeling as possible and try to do really what we call an ab initio, or from first principles understanding of this system. So without any prior knowledge or any kind of input from experiments. For example, in this case here, just an idea that is interesting is that, for example, if you take platinum and you try to wet platinum, depending on the surface that is exposed, then platinum can be a hydrophobic or a hydrophilic surface. So you see, you take the same material and you try to wet this material, and depending on the surface that is exposed, then there will be wetting or no wetting. So all these things is things that we try to understand. But what I'll be focusing here is not really on this interaction, but just looking at water itself. And water itself is already a very, very complicated material to look into. And the reason, one just example is that this is the phase structure or phase diagram of water, and we are basically here. So water is a liquid, thank God. But if you increase the pressure, or if you increase the temperature, it will become a vapor. But if you decrease the temperature, or you increase the pressure, then all this region here is actually ice. And what happens is that we know this graph is actually already outdated. Because of these very complicated interactions in water, we now know that there are at least 20 phases of ice. Right? So there are at least 20 forms of water that can be organizing itself in different crystallographic structures. And now, the most common one which you get in your fridge is what we call ice IH, which is here. But you have all these other ones, and the other ones that are maybe not shown here are usually very high, very low, very high pressure phases, which are showing up in this region here. So, why is this, right? Why is water so complicated? And actually, this is quite a good thing. This is the reason why we have life on Earth, is because of this complication in the phases of water. And the reason for this is because if you look at the molecule and how the molecule...
Those other phases, 6 and 7, do we have them on Earth?
Here. Yes, I think so. Yeah, GPA. One GPA is actually you can get deep down in the ocean. Yeah. So, for example, if you're looking for these other phases of ice, that some of them will show up in like very high pressure conditions still on Earth. But also, we expect some of these phases to show up in outer space. And this is also, I mean, some very hot topic in astrophysics is to understand what is happening to different phases of ice in other planets as well. Okay, so what is the reason for this? So, as we know, water is a very simple molecule, is H2O, so 2 hydrogen atoms, 1 oxygen, so not heavy atoms. And I'll try to show you that also this is a complication to have hydrogen. And then you have a balance of interactions. So the molecule itself is bound by covalent bonds between the oxygens and the hydrogens. There's also some charge redistribution between these molecules, these atoms. So there's what we call a dipole moment. So there's a little bit of charge moving from the hydrogen to the oxygen. So there's a charge imbalance there. But also, there's interaction between the molecules, and so you're forming, the hydrogens interact with the oxygens from an extra molecule, giving you what we call hydrogen bonds. But also there's another type of interaction which was called van der Waals interactions, which is essentially a dynamical correlation interaction, which is only coming from the fact that we have quantum mechanics. Also, the covalent bond is also coming from quantum mechanics. But anyway, the other issue that happens here is the fact that everything is quantum mechanical, and in actual fact, the hydrogen atoms are very, very light atoms. And so not only, typically what we do is we simulate things, or we calculate things considering electrons to be a quantum mechanical entity, but we also have to consider here that hydrogens are light, and they also have to be treated as quantum mechanical entities. Okay, so this is essentially where we at, right? So we have this molecule. It seems simple, but it's actually very complicated. And we want to understand what's happening at the atomic scale. And the good news is we know the rules of the game. And if you're a physicist, you know that essentially quantum mechanics governs the interactions between electrons and protons and nuclei in essence. And in actual fact, so physicists are very obnoxious people. And in 1929, Paul Dirac, which is one of the most famous physicists in the world, he wrote a text, and he was basically saying, okay, we have devised quantum mechanics, so by 1929 we more or less figured out, the rules of the game. And he wrote a paper saying, okay, so we have this, basically chemistry, most of physics, and chemistry is all known now. We have finished everything. He didn't even bother about biology here. So he was saying, okay, but the problem is that now we have these equations that govern the nature. However, solving them is extremely complicated. And essentially what he's saying is that what we have here is going to be emerging from this complexity. And whenever he says it's too complicated, it means that we'll never solve it. I disagree. We can, in principle, eventually solve it. Basically saying, okay, there are things that are going to be showing up here, which is, very complicated, but we know how to play. It's like we know what are the rules of chess. However, the possibilities of a chess game are almost endless, and so everything can happen. And essentially, this is what he's saying here. Okay, so we know that quantum mechanics is governing everything. People have done a lot of contributions towards this over the years. But basically, what we can say is that the entity that describes a set of electrons and nuclei is what we call a wave function. So basically what we want to do is to try to find this wave function for a system of a very, very large number of particles. And this is basically what we're doing, we've been doing, like computational physicists have been doing for quite some time, working in materials, is we want to understand a system formed of various atoms and formed by nuclei and electrons. We try to use quantum mechanics to do this, to solve this. Because these equations are extremely complicated, we need very, very large computers, and this is really like a bottleneck for especially people who are in a third world country, a developing country like Brazil. It is that obviously we are lagging behind other developed countries which have a much, much higher access to computing power. But anyhow, it has been improving in Brazil. We have some access to a few initiatives by the Brazilian government. Also, the state of São Paulo is funding some high-performance computing centers. And from this, we try to infer information about macroscopic properties. Right. So this is essentially what we do. And obviously, there is a problem. So we have these computers. However, as I was saying, things are extremely complicated, and so we need to do approximations, right? So if you're a physicist, although you're extremely obnoxious, what you usually do is you try to approximate things by the simplest possible way. And so, the running joke is that you try to approximate a cow by a sphere. It works sometimes, other times it doesn't. But this is what we need to do. Otherwise, things are extremely hard to do. And in actual fact, although everything is quantum mechanical, what we usually find is that for the movement of atoms, once you know how these atoms interact, classical mechanics works just fine for movement of atoms. So in actual fact, what we want to do is to find the interaction between how the atoms interact between themselves, and then essentially find, evolve this using Newton's second law, F is equal to ma, to evolve these things in time and try to find the time evolution of our particles. And in essence, for example, for us, if you're looking for water, it means that you want to do the interactions between the hydrogens and the oxygens, and obviously between the water molecules amongst themselves. And then you just let this liquid, or the solid if it's ice, evolve in time. So from from a physicist perspective, what we want to do is write everything in terms of equations. And so basically what we can say is that everything we're trying to find is something called a potential energy surface. So potential energy surface is exactly describing, this interaction in time on a very, very complicated, multidimensional function. But in principle, once you have this very, very complicated multidimensional function, then everything is more or less solved. How can we do this? The simplest possible way to do it is to say, okay, I construct a model. So basically it's, taking my cow and writing it as a sphere. So I say, okay, the interaction between two atoms in a covalent bond is like a spring. And then I can have interactions which are these bending interactions between the atoms. I can have torsions, and then I model this with these parameters, and I try to find some fitting parameters for this based on some other calculation or some experiments. This is what we call a classical method, and it's classical because you're obtaining this information from somewhere else and then fitting it, and then we evolve this classically using Newton's second law. The other option is actually to really go back and say, okay, everything is really quantum mechanical. And so we can do this very, very, very accurately in principle. And here, I'm not going to really say much. There's a technicality. We forget about this idea of using a wave function and move on to something called density functional theory, which is much more, it's an equivalent formulation of quantum mechanics, however, much more efficient. And so, in actual fact, this guy here, Walter Kohn, got the Nobel Prize in 1988 exactly for, making these things calculable now. So we can really do materials because of him. So we get, essentially the same thing. We get, we can calculate the properties of a system, a quantum mechanical system, get the information about, how the electrons are rearranged in a certain atom. However, there are approximations that need to be done when we do this. So again, complexity doesn't come very easily. We need to do approximations here, and then we do include these different degrees of approximations. Things become more complicated, more expensive computationally. However, in principle, we get more accurate results. So we don't have, although we have in principle the underlying theory for calculating things, we don't have the exact recipe to calculate things. We do everything in still an approximate way. Okay, so basically we have two competing type of approaches. We have an approach which is what we call the classical method. Because everything is classical and parameterized, it's very, very fast, so we can do simulations of millions, even billions of atoms. So we're reaching the point where people are here and they're already trying to simulate something that looks very much like a cell, right? So this is the level of quality or size of simulations that we reached at this point, right? With all the atoms in the right places, right? So you're really constructing, biological structures using this type of approach. Or you can really do quantum mechanics, which is very, very accurate. However, you're limited to about 1,000 atoms at best, right? So something that maybe if you're a chemist, that's reasonable. If you're a biologist, then obviously that means nothing. What we would like to do, we would like to get the best of both worlds, right? So we would like to have something that is fast and can tackle large systems. However, we want to do something that is very, very accurate at the level of these quantum mechanical methods. And most importantly for us is actually to forego a model. And what do I mean by forego a model? It means that, in a sense, I don't have to worry that there is an underlying physical model that is describing my system. So I don't really want to worry whether, I'm modeling my cow as a sphere or as a cylinder. I don't have to worry about that. All I have to do is to set up my calculation and run it again, as I would say, from first principles. And obviously that is accurate. I can actually do predictions. So how do we do this? So the latest fad is machine learning. And obviously we want to jump right into it. So, but if you're a mathematician, you would say, we've been doing machine learning, or we've been, we have the theory of machine learning for a very, very long time. And in actual fact, if you go down to, if you think about it, it's essentially some form of very, very non-linear regression, right? So it's a very, very rudimentary, or not rudimentary, but very, very complicated way of doing curve fitting, right? This is basically what we're doing as well. We do this machine learning. There are various methods. You can start from doing a linear regression, and you can call it machine learning, or you can go towards what we do, which is called a neural network. So what is a neural network? So neural networks are based on this concept of neurons. So you would have a unit called a neuron that is somehow connected to multiple other neurons, and you have then an entry point for this neuron, and this neuron might or might not fire depending on the type of entry that's coming in, right? So basically you have multiple possible entry points to this neuron, and then depending on what is actually input into this neuron, somehow this neuron either fires or doesn't fire, right? And if you have to connect these multiple neurons in a very complicated way, or even in a very simple way. So for example, this is a totally connected neural network, because every neuron on one layer is connected to all the other neurons in the next layer, and so on and so forth. Right? So this is kind of the simplest possible way you can think of a neural network. And then obviously you can look at what is the structure of the neuron. So basically you have, you can have multiple ways of inputting this signal written in a mathematical form, and then you have an output, right? And then the output will be used as an input to the next neuron, and so on. And the beautiful thing about neural networks is actually what you call back propagation. So you can actually have information not only about going forward, but you can actually go backward, and also there's information in that as well, once you have your neural network set up. And it's also a way of actually doing the training, and I'll talk a little bit about this in a second. Now, because of this idea of firing or not firing, then obviously the neuron is a signal, right? So the simplest possible way is you say, okay, if you reach a threshold, then the neuron will fire. If it doesn't reach, then it's 0, so it's a 0 or 1. Usually we don't choose this type of function, 0 or 1, like what we call a step function. We choose something that is smoother, and this is because you can differentiate this function. And so obviously from a mathematical and a computational point of view, things become much, much simpler. You can choose different types of functions to do this type of firing. And obviously then it becomes a little bit of a black art, and you have to try different types of functions. Some of them work for different problems. And so whenever I said, oh, we want to forego of a model, actually this is not completely true. You have to choose what is the firing function. You also have to choose the topology of your network, so how these neurons are connected. However, one interesting aspect of these neural networks, and why we choose neural networks, is because there is actually a theorem saying that given that your function, in our case a potential energy function surface, is relatively smooth, then there exists a neural network that will actually represent that function. So there's an existence theorem that will actually indicate that there is a way to exactly describe that potential energy surface. So there is a way to actually solve the problem. However, for a mathematician this is great, for a physicist not so much, because there is no recipe to get this function. So I don't really know how to actually set up this neural network. And so again, becomes a little bit of a trial and error to actually set up what is the neural network that gives you something that gets as close as possible to this potential energy surface. Right? And again, unfortunately, there's no real recipe to set up this network, but we have some idea, and it's usually based on physical intuition, and so we set up different ways of doing this. Okay, so in our case, for our system in particular, we need to do is, first of all, understand what we're trying to get out of this network. And the information that I want is, I would like to put in the distribution of atoms, and from the distribution of atoms, the network will give me the forces that are acting on those atoms. Because if I get the forces, then I can move the atoms to the next step. The next step will give me again a set of structures. I will get the forces out, and so I can get a time evolution of my atoms in real time, in real space, right? So I can really see the water molecules moving inside my system. So we need to do this. So the information I need, which we call descriptor, are the positions of the atoms, or the relative positions of the atoms. And then from this information, we train a network. So the first step is actually to train the network, and I believe Vanderlei gave a very nice, idea that the first thing that you need to have is a good data set, right? So if you have a good data set, this is the first step, and it's really, really extremely important. So if the information is not out there, then obviously whatever you put into your network will be crap coming out, right? And obviously this is the reason why Microsoft, Google, everybody is interested in your data, is because now what they want to do is to use your data to build up very, very large data sets of everything, to provide this to companies that will use your data, not necessarily your data, but the general data of the person, to try to predict things that people want, right? So this is really, really a key issue here, and that's really why all these companies are interested in information, gathering information. So this is what we do. We build a data set that in our case is a data set for water and ice. And first of all, we need to do a very nice sampling. So we need to put, find a way to put the molecules in a very, very good different positions to get a very nice description of what we call phase space, right? Once we do that, then from a subset of these structures, we do very, very accurate calculations based on these quantum mechanical methods. And so from these very accurate calculations from quantum mechanical methods, we obtain, so from a set of positions, we get forces. And this is what we use to train our network. So our network basically means I introduce positions into the network, like the network is initialized without any information, and then it gets the forces. And then I check whether these forces that are coming out from my network are actually equal to the forces that were calculated using my very accurate methods. Usually in the beginning they're not. So then I do this back propagation, and then I change a little bit my network, and then by changing a little bit my network, I look for a better description of those forces, and I do this many, many, many times until whatever I put in gives me forces that are equal to the forces that I want, right? And then by this, I consider my network is trained. And then I test whether by taking a set of data that the network has not looked into, then I compare this, I feed into the network, and I compare it to see if the forces are relatively the same still, right? So I ask the network, you haven't seen this data yet, try to predict the forces on this data. And because I know what the forces are, then I can do a comparison. And so we do this, so our networks are trained using this method. So just a little bit of detail. So our network is what we call a deep neural network. So our network has multiple layers of neurons. And in our case, we find that we have a neural network that is a kind of a triangular shape. So we start with very large number of neurons on the first layer, then decrease the number of layers as we go along. And with this, we get actually very, very accurate description of our system, and then we can do dynamics. So we can really look into the movement of the atoms into water and ice. This is more technical, so you basically look typically in how you can actually predict your forces and energies and see if they're within a reasonable error. In our case, they are. And then by doing this, now what we're doing is we take this and now we try to understand from ab initio, so we're not inputting any information from experiments. We want to know whether we can actually get macroscopic information. So for example, the density of water. So we do a simulation of water with a certain number of water molecules. In this case, about 1,700 molecules, which is already enough. Even 64 water molecules for the density is already enough. And we get, depending on the level of approximation, so these are different levels of approximation that you use in your calculations. So our data set, so each one of these is a different data set. And we can see that we get an error that can vary between 10%, which is already very large. But for example, for this data set here, which is probably the best data set that you can have, you get an error in the density of about 2%, right? Which is a very good number. And this again there's no information about the actual density of water in this case. Right? We didn't start with prior information. Okay, and then what we look into, yeah, sure, I'll end this quickly. So one of the information which I mentioned was, okay, so we want to look at the structuring of water. And so if you look into a liquid, so what is the difference between a gas and a solid? So a crystal. So if you look at a crystal and if you look at the positions of the atoms, then they're very well positioned in space, right? Whereas in a gas, they're completely disordered, right? So one way of looking into this is what we call a radial distribution function. So essentially what this radial distribution function is that given an atom in a certain position, what is the probability of finding another atom at a certain distance r from that position? So for example, in oxygen, so if you look at two oxygens, then this is the typical first layer of oxygen in water. And so if you had a crystal, what you would see is peaks. If you have a gas, you would see a flat line. So a signature of a liquid means that you have something that has structuring at short range, and then as you go towards longer range, then it becomes essentially flat. Right? This is a signature of a liquid, and so the gray line here is what you get from experiments, and in actual fact, it's not very, very good if you look at the peaks here. But the worst part is if you look into hydrogen. So in hydrogen, hydrogens are very, very localized. Right? And they're very localized exactly because we're considering the hydrogens as a classical particle. In actual fact, if you try to look at the diffusion of water, so extremely important piece of information is how water diffuses within a liquid or within itself in this case. So it's the self-diffusion. So this is the experiment, and whatever we do, we get something that is at least 5 times smaller, 2 times smaller than the experiments. In order to solve this problem, you really need to consider that the hydrogen is also a quantum particle. And if we do this, there's a method to do it called path integral molecular dynamics. And then if we do it, you can see that the peaks are actually much, much closer to the experiments. And even the oxygen ones are closer to experiments. And then if you consider them quantum particles, you can see that the diffusion of water is spot on for these cases here, and also the viscosity of water is also spot on. So you really can we can actually map this into the experiments, again, without any prior information about the experimental setup, only the temperature and the pressure, which is coming from the experiments. I'll skip this because it's more technical. And then going to ice, just to finish, we can do the same type of things with ice. Again, our network can work with both. And what we looked into is actually one of the phases of ice, the phase that is most common, which is ice IH. And then it's an hexagonal structure, and we look at the density of ice. Now, for ice, things don't get very well. We get an error which is actually of the order of 6 or 7% at best. The other problem is that depending on the level of approximation that you use, and this is not really from the network, it's coming from the calculations that you use to build your data set. Actually, ice shouldn't float, so obviously this is completely wrong. But in other cases, ice does float, but we get an error. And when we treat our nuclei as quantum mechanical particles, actually we get even worse. And this is indicating that the quantum mechanical calculations that we're doing are still not accurate enough. And this is really highlighting the importance of the data set again. So just to finish, we understand this because there's an increase in the density of ice, and decrease in the density of ice is actually coming from an increase in the interaction between the molecules. So the van der Waals interaction actually increases, and it increases even further if you consider these quantum mechanical effects. This is actually different from water, so there's again a kind of anomaly behavior between ice and water coming from this effect. So water would not see this increase in interaction because of these quantum effects. But and also clusters of water will not see this, and so we see a strengthening of these van der Waals interactions in ice, whereas in water there's a weakening of van der Waals interactions whenever we include these nuclear quantum effects. We actually quantify this so we can get any information. So this is the first time you can actually get information about the energy of interaction between water molecules in ice coming from this van der Waals interaction. So it's of the order of about 250 milli-electron volts. And also we can quantify what is the increase by including quantum nuclear effects. And so just to finish, what I wanted to convey is that we can use these neural networks or even different machine learning methods to get structural information from an atomic perspective, in principle without any need for experimental input, right? Which it doesn't mean that we don't need experiments. On the other, it's not really that. What I mean is that what we can do now is that we can really do a comparison between theory and experiments without any kind of feedback, need for feedback. So in a sense, we can know where the problem is, whether it's in the experiment or in the theory. And also, obviously, that we have these very important interactions coming from these nuclear quantum effects, which, again, because we can use these neural networks, we reach the point where we can actually include these effects because calculations become extremely more complex and more heavy by doing this. And with this, I would like to thank my collaborators, especially Lucas, who is my PhD student and was involved most of this work. And Luana is a professor at USP. Mariana, where I spent my last year at the Max Planck in Hamburg. Now she's moving to a chair in Cambridge, which I'm really happy because I actually, whenever I came back to Brazil during my PhD, I was working together with Mariana at USP, and then obviously she moved on, and now is getting a very, very prestigious chair at Cambridge. And Márcio is at UFABC, and my postdoc, Alberto. And with this, I'll thank you and thank the people who paid the bill at the end of the day.
Thank you. So, if I understood correctly, the next speakers need to connect their own computer, right? Maybe the students can, yeah. You can start. So I think we have time for one or two questions. So if any of you wants to say something.
Thank you so much for this wonderful talk. I guess I had a question about. It's just fascinating to be able to understand a system at that level. You mentioned initially that you cared about the interaction between water and surfaces. I wasn't sure if the results you were showing was about that interaction with the surfaces.
No, not yet. I mean, we have been working on the surfaces interaction as well. We have been working on the surface interaction as well, but I wanted to just focus on the other ones. But what happens? So just a pinch. So what happens in surfaces is that water will structure even more on the surface. And so what we're interested in is, again, depending on the type of surface, whether you have different types of structuring. And what we really want to do is, what we're doing is to see whether, you have, depending on the type of material that you have, whether you can break water and lower the barrier to break water.
And just one more really quick, because it's interesting, and I'm sure that step by step in terms of complexity, I've worked on wettability for biomaterials, and the difficulty we find is that many of the biomaterials that are actually useful in the human body are very complex in the surface, right? So we're adding nanostructures, they're micro rough, and so I would love to talk to you more in detail. We came out with this paper a few years ago, trying to understand why is it that high hydrophilicity seems to be very good for biological performance, and we think it has to do with air contamination. So basically air bubbles that trap in the surface. And I wonder if your model would be able to look at that as well.
In principle, so we definitely have some things on we can talk more. We were interested at some point on detecting DNA on surfaces for another project for a very long time. And so we looked into a little bit of, surface attachment of DNA on at that time was graphene, but in principle we can simulate other materials as well. And this is something that we really would be interested in.
Any other question? Yeah.
Good afternoon. Thank you very much for the talk. The problem of surface is also very interesting, but what about the description with this methodology of double layer effect, for example, in electrochemical system, and also the light or electromagnetic interaction in photochemical systems for description of bone-broken chemical reaction?
Yeah, that's a very, very nice question, actually. So, on another project that does not yet involve machine learning, what we're interested in is exactly the double layer formation. So, in that case, what we're interested in is how do you simulate when you actually apply an electrochemical potential in the system, right? And then you have everything in a solution. And then you look into the formation of the double layer. So basically you charge one of the surfaces and you try to see what is the reorientation of the molecules plus this the formation of these kind of positive and negative charges on a very small range around that thing. So we're interested in that. We haven't really reached that point yet because it's a different type of theory that we're using, and then it's a much heavier calculation. But we definitely would like to look into that, and we're looking into that. So right now what we're doing is we can do one molecule on a surface.
This is for the future.
Yeah. But we're planning on that, yes.
Thank you very much.
Well, thank you, Alexander. Thank you. Thanks again. The next speaker is already here, but I think we have 5 minutes break just to go.
Qual vai ser a melhor escolha? Aqui no IMAC.
sala era? Yo te cuento después. Mis historias siempre son muy cortas y sencillas.
Tem café, será? Tem café?
Como los gatos de Santa Oca. Sí, sí. Si ustedes tienen más, entonces... No, pero
Centre, oops. Not working, yes. Centre International de Mathématiques Pure et Appliquées. It's a French association. The headquarters is in Nice in France. And I am currently serving as president. And Christoph Gritzenthaler is the director of SIMPA. He's the person, the man on the road. He's the person, the hands-on person in our organization. Okay, so this is a very nice slide. This presentation was actually partly prepared myself. Okay, SIMPA is. Its mission is for broad access in mathematics in all developing countries and another way to share research. Okay, so SIMPA was founded in 1978 in France, and let's see, it's a non-profit organization. Its main mission is to promote research in mathematics, not just mathematics, but research in mathematics where research in mathematics is being developed. Okay, so we need to have critical mass, okay, we need to have something, but we need to be underdeveloped, okay? Okay, so it holds activities in various countries around the world. It's a global organization. And the main activity are the SIMPA research schools. It's the historical activity of SIMPA focuses on areas where there is real drive to develop mathematics and where there is a scope for a research project. Okay, so this means that SIMPA research schools are research topics. They're not courses like for master's or PhD level. They are research schools. They take place on topics that are currently of interest and under real development. Okay. Another activity, another sort of historical activity, are the SIMPA courses, where a guest lecturer goes to a university somewhere in the developing world. Give a course. These courses can be anywhere from, let's say, a week to 2 or 3 months. Okay. And then there's newer activities, the SIMPA fellowships and the research in pairs. Okay, and I'm going to be talking about that during this lecture. Okay, so and the other activity that we have are the schools in partnership. Aside from these activities, we have been establishing specific agreements with different institutions around the world. Okay. Here we are, SIMPA. Its mission to promote research in in developing countries, in mathematics in developing countries. It is a UNESCO Category 2 center. This is very important. So we have sort of a stamp, a quality stamp from UNESCO. Okay, but we're fairly autonomous. That's what the Category 2 means, that we're fairly autonomous. It's a non-profit French association. Here's the website, which you can go to. It's currently being under renovation, so there's still some things missing with regards to the old website. One very interesting thing about SIMPA is that we have only 3 employees. The whole organization, it's a huge organization, as you will see, and it only has 3 paid employees. The executive director, that's Christoph, he's the person on the ground, an executive secretary, and a communications officer, and it has a budget of about 700,000 euros yearly. Okay, this is yearly. Okay, we have about 140 individual members of SIMPA. These are people, okay, individuals, and 28 institutional members. And we receive funding from 5 different countries. France is the main the main revenue comes from France, Germany, Norway, Spain, and Switzerland. Okay, so it's very, very integrated organization also. Here's an organogram of how things flow in SIMPA. So the deciding body of SIMPA is the General Assembly, which meets once a year. Okay? The General Assembly has all the institution and individual members. They're invited to attend. Okay? We've been having meetings, these are hybrid, so sometimes we have them in person, sometimes we have them fully virtual. The General Assembly is informed by the governing board. The governing board has 7 individual members and then 7 members from the administration of SIMPA. The administration of SIMPA is made basically by the bureau or the executive committee, which consists of the president, the vice president, the treasurer, the secretary, and the executive director comes. The president, the treasurer, the secretary, and the executive director comes. He basically sets the agenda. He tells us why we have to meet and what we have to discuss. Sometimes we actually come up with ideas too, but mostly it's at his behest. Okay, we basically meet once a month. Okay, and then there's the executive team, which is the executive director, which is Christophe currently, a secretary. This is Agnes Gomez, the executive secretary, communication officer, and a team of scientific officers. They oversee the day-to-day operations of SIMPA. Okay? Then the proposals for SIMPA schools, SIMPA courses, fellowships, research in pairs, all the different activities that we have are evaluated by the Independent International Scientific Council. It says approximately 12 members. Currently we have 14 members of the Scientific Council, and they meet online and then in person once a year also. The Steering Council meets once a year, and the main reason for the Steering Council for the meeting is to make decisions regarding the SIMPA schools. Usually we have anywhere between 20 and 28 SIMPA schools per year. This number fluctuated lower, of course, during the pandemic, and now we're back to the usual levels, basically. Okay, the Steering Council is enormous. It has all the individual members of the governing board, plus all of the executive team. That means all of the scientific officers. There are about 15 or 20. All of the institutional members, and then there's a bunch of dignitaries, members from the various states that contribute to SIMPA. Here's the new governing board, which took office in January this year. Myself as president, Sophie Gaboyan, he's from Université Côte d'Azur in Nice. That is the headquarters of SIMPA, and he's there as our treasurer. Secretary was treasurer. The secretary is Jorge Bosa Fernandez from Valladolid in Spain. And then, so these 4 comprise the bureau, and we're the ones who meet once a month, okay? Aside from this, we have the individual members, Cécile Armana from France, Université Paris Pasteur, Patrick Chempo, I never know how to pronounce Patrick's name, from Northwest University in South Africa, okay? And Raim Zahar-Nahandi from University of Tehran in Iran. So it's a very international governing board as well. So we met in January. In fact, we met back to back. First the governing board, then the steering council. Here's a picture of our meeting of the steering council, and you can see that it's fairly big. There were a lot of people, and then there's a lot of people online as well. Okay. Let me tell you a little bit about the Scientific Council. We have just renewed the Scientific Council. So the rules of SIMPA are that all terms, president, vice president, all bureau, governing board, Scientific Council, everybody who is elected, these people serve a term of 4 years, renewable once but not twice. Okay, so at most you can serve 8 years on SIMPA. I was on the Scientific Council for 8 years. Okay, so our Scientific Council is chaired by Julia Di Nuno. She works in financial math and stochastics in Norway. Then we have Volker Bach from Germany, TYAN Din from Singapore, Mithili from India, and Yoshiko Hoyaka are here from Brazil. So these are people who are starting their second term on the Scientific Council. Again, please note the very international flavor. This is the new members of the Scientific Council. Cyriac from Benin, Christian Blanchet from France, Lara Bossinger from Mexico, from Switzerland, Alicia Dickenstein from Argentina, Alio Diop from Senegal, Carlos Perez from Spain, Tim Romer from Germany, and Aisa Wade from the United States. Okay. We tried to have a very broad people in terms of fields and also geographically, and also a nice gender balance. Okay, the Scientific Council meets once a year. This is the meeting, the picture from the meeting of last year, the old Scientific Council. Several of the people here have not renewed for their second term, and a few were already in their second term and had to be replaced anyways. Why cooperation in mathematics? Well, math, as we know, is everywhere, and 3.5% of the yearly scientific publications, 90% of them by 12 countries, and what about the other countries? Okay, so again, we need to not waste talent, okay? So this is very timely, and it's very much in line with UNESCO's Sustainable Development Goals. For instance, math is a central tool for research and innovation, and that's one of the Sustainable Goals is to strengthen scientific research. And so in 2019, we had 21 SIPA schools, that was before the pandemic, 30 SIPA courses, 17 schools in partnership, and 10 SIPA fellowships. Some of them, here's some of the places where they took place: Cuba, Cameroon, Iran, and India. It's really a very, very international organization. SIPA promotes development with respect to gender equality also. All of the applications to schools must have at least 30% women and 30% men among organizing scientific committee, lecturers, and participants. Okay? Almost all of SIPA support is directed to participants from developing countries. It's very important. So when you apply to a SIPA school, the SIPA funding only goes to students and students who are from developing countries. Okay. The lecturers are expected to be self-funded or have some other kind of funding, but SIPA does not fund the lecturers. Okay. And SIPA promotes relationships between mathematical communities in the world. So that's the Sustainable Development Goal 17.6, reinforce access to science, technology, and innovation, and cooperation north-south and south-south. Okay. We have local impact in the long term. So this is not isolated. Okay, so we coordinate activities and we build long-term programs. We also develop strong local educational programs. We have some specific agreements. For instance, the International Masters in Mathematics in Algeria comes to mind. New program, new agreement now with Vietnam, also with the Vietnam Academic Science and Technology Center. We encourage colleagues who choose to work through the SIPA fellowships. They go to Europe for a period, and then they go back to their own countries, for instance. Same thing for the Research in Paris program. And SIPA is very concerned with reducing carbon footprint. That's one of the reasons that we've moved many of our meetings to be hybrid or even completely 100% online. Okay, how do we work with developing countries? Well, this is a European organization. Okay, so mathematical unit up here at the top. Which ties in with the European Math Society, and ERCOM, which is the organization within the European Math Society, which funds programs in developing countries. And then there are partners, SIPA, ICTP, and the ICMS in Edinburgh. Okay? The European Math Society has a specific committee for developing countries, which also partners with SIPA in many activities. The International Mathematical Union, the CDC, the Senate Committee for Developing Countries. One of the members is Andrea Solotar, okay, who also has a very strong ties with SIPA. How do we decide which countries are developing countries? Easy. We simply take the table, which is made by the IMU. Okay, so the definition of the IMU is if the GNI per capita is less than $14,000 or less than $20,000, but research and development spending is below 1% of the country's PIB.